and computer science at the University of Berkeley. She's also an RSA professor of EECS and world-renowned expert in cryptography and AI security, recipient of the ACM Turing Award in 2012 for her work in revisualizing the science of cryptography. Professor Goldwasser has also been a member of ADIA Lab Advisory Board since 2022. And we are honored to have her back with us today. Please welcome Professor Goldwasser.
So hi everyone. We are a small but high quality audience here. I have like my two Nobel Prize winners who have come to cheer me on. But I want to warn you that this is not a whole visionary talk about the future of AI and economy, or future AI in physics, or future in AI with climate. It's a very specific talk about some of the work that I've been doing in this area. And what do I mean by this area? Hopefully they have my talk here. There's a new version, but you'll see the old version. Right, so the specific topic is about a robustness and alignment for machine learning models. So, by the way, my affiliations have changed. I'm not in ECS, I'm in mathematics department at MIT. But in any case, so this is just after all we've heard and all the possibilities that AI can do for us, there's just a few questions for the thinking person, man or woman, and can you always distinguish between AI hallucinations from truth? I think the answer is no. Do we understand why AI works? I know the answer is no. Is there sufficient oversight of AI? No. Is AI built by altruistic organizations? No. So if you think about it, and the answers to all these questions are no, there is no oversight, sometimes doesn't say the truth and you don't know it, nobody understands why it works. Maybe the conclusion, well, one question we should ask ourselves, should we really use these models in all these 7 areas of life when we don't understand them nor control them? You can decide for yourself, but it's really a mute question because it has been already used in so many industries, infrastructure, traffic patterns, energy usage, autonomous vehicles. In San Francisco, it's quite common. I think people prefer to take Waymo than other Uber drivers because nobody talks to you and bothers you, and they drive more safely also. And health and drug discovery, that's a big promise. I'm actually very hopeful. Protein folding, financial institution risks, fraud detection, policing, predict which neighborhoods to police, law. I was just in a conference on law and AI, and they start talking about using it as an aid in many different industries, and maybe enabling people who cannot afford lawyers some quicker access to some judicial or tax advice. Okay, in any case, what this tells me though, given the first slide, okay, so that on one hand, we don't really understand these models and we don't control them. On the other hand, it's going to be used, and it is already being used, is that the focus that people in academia can do, certainly people in my field, is on doing research on achieving reliability and trustworthy AI whenever possible. Okay, so that's the focus of my research in the last few years. It's also very fertile ground to ask questions and to use methods that I'm comfortable with. All right, so with that in mind, what are some of these trustworthy AI challenges? Because you need to define them in order to solve them. So this is maybe the most useful slide in this talk, and then later I'll tell you a little bit about what we've done in each one of these areas, or at least 2 of the areas. So privacy is the most obvious thing, and people have talked about it in this in these last 3 days, time and time again, because training data often is data which is owned by individuals or companies or whatever, and they sometimes even legally protected. You want to protect the privacy of the data during training. Then verification. What's verification? People don't talk about that much, but since the models are trained by, let's say, companies that you're not an insider there, you don't have control over, and somebody gives you a model, it would be fantastic if you could develop methods to verify the properties they claim to have. What kind of data usage? Do they have bias? Are they accurate? And even better would be that whenever you ask a question, you get back an answer, that there will be a way to verify whether the answer is correct or not very quickly. Now, of course, this begs the question of what does correct mean. In mathematics, it's clear what correct means. In the science, it's a little less. And certainly when you get to things like, give me advice about my love life, I don't know what incorrect means. But there are lots of actually questions and answers that you get that still are not correct and you could verify. You know, things that rely on sort of database of facts and things like that. So parsing this, putting it into a format where you can actually verify quickly is an interesting mathematical question. And we've done some work on that. Robustness, what is robustness? Robustness is you're training on some data distribution. It could be, I don't know, MRI slides. It could be all kind of health records from the past. Could be financial records from the past. But, you know, this changes. As we know from the pandemic, you know, the health data changes radically for people who've had COVID. There's been a lot of rise of autoimmune diseases and things of that sort, whether it's from vaccine or not vaccine, God knows, or maybe even God doesn't know. If there is a God. Okay, anyway, we will, so the question is still, what guarantees can you make? When you're training on data, what guarantees can you make on future data distributions? Can you raise a flag and say, you know, the distribution that you are interested in now is very different than I've trained on, so take it with a grain of salt. Can you detect when somebody's adversarially trying to manipulate your model? Or can you even worry about and do something about when there's insider tinkering in models? So I know in Google, I'm sure it's everywhere else, but in Google specifically, there's a lot of worry about insiders who are trying to get information, who might be modifying, and what do you do with that? Is there a way to detect that? Is there a way to mitigate it? Then the next thing that a lot of people are talking about now is all of this was like about classification models. Models who tells you yes, no, buy, sell, yes cancer, no cancer, accept a school, non accept a school. But now all the raves on language models, which are amazing. But one of the big questions people talk about is alignment. I'll talk about this a little more in a couple minutes, but just for now, in case you lose attention, which happens. Alignment is the question that you have an LLM and you don't want it, you know, they don't define it. It's very informal. They say it should align with human values. Now, human values change all the time, as we know. Human values now in the US under one president are different than human values in the previous president, and you rename everything instead of DI, you call it something else. But in any case, alignment with human values, best examples are if you ask a language model advice of how to do something criminal, how to make an atomic bomb, how to attack someone, how to take over a plane, it shouldn't answer. Or how to commit suicide, it shouldn't answer. And the question is, how do you guarantee that? How do you actually filter for these type of questions? Not an easy question. It's quite interesting, the ingenious ways to get around whatever guardrails these models utilize. And another question, for example, you could ask is how to prevent model stealing. I know that when DeepSeek came out, there was a lot of conjectures about that it was used by using OpenAI. And I think there's this famous kind of funny incident when in the beginning they asked him, who are you? And they said, I'm ChatGPT. So it was like, okay, if you say so. But there's a question of watermarking, LLM outputs. So all of these are, I would say, under trustworthy, is ML, machine learning, trustworthy category. And today I will speak on these three: verification, robustness, and alignment. And because I think I originally thought I had more time, I'll start with robustness and alignment, and probably won't get to verification, which is maybe the more interesting one. Okay, so the one thing, because I'm a cryptographer, and we always think worst case, is that we think always to model these questions that I asked in the previous slide with respect to a worst case adversarial attack. So we're not saying, we don't know the attacker is going to behave in a certain way. Obviously, that if you get a positive result, that's a much stronger result, because it says in spite of what the adversary would do, whatever bad strategy, we're prepared. So the one assumption we usually do make is that the adversary doesn't have exponential time. So there's sort of polynomial time, reasonable amount of limit on the running time of the adversary. Of course, if you prove an impossibility result, so if you say it's impossible to protect against a worst-case adversary, then you might consider a limited adversary with limited capacity and prove results. This is all cryptographically inspired. As I said, as a cryptographer, we always think about worst case because you cannot say cryptography is secure, assuming that the adversary only does very limited things. Okay, and this is, I think, a slide I used also last year, but I still believe in it. And that is that we have sort of a recipe in cryptography for doing this, and it's a useful recipe. It's really developed a field. This prove is really 1.0. It's my mistake. Although it's a long process. So it's a prove. So anyway, the recipe is, you want to model the adversary very carefully. That is, yes, okay, it has restricted amount of time, but what are their capabilities? Can they modify? Can they just look? Can they leak? Is there partial leakage from secret keys? Whatever. So you want to model, then you want to define what is trustworthy for you. It might be indistinguishable from something that's really trustworthy. It might be approximately trustworthy, but as long as you define it, and then you build a solution, you're supposed to prove, and that's very important, so the emphasis is on theory and proofs, is that the solution is trustworthy. And if you make assumptions, you have to make them explicit, and hopefully the less assumptions you make, the better you are. And the kind of assumptions usually is some problems hard to solve. If it's a classical computer, let's say factoring is hard. If it's a quantum computer, could be another problem that's currently hard for quantum computers. You might have several parties participating, and you want to say that they don't all collude, so you are assuming separation. You might have trusted hardware. So I think that the lady that talked this morning, she was talking about this type of approaches for achieving privacy. Okay, and sometimes you cannot solve it. But then it's actually been interesting that you could use assumptions in cryptography to show that something is impossible. So in some sense, if it was possible, you would be able to break cryptography. So you're using this kind of methodology both to come up with solutions or to show, listen, you're barking up the wrong tree. You're not going to be able to solve it in the way you defined it, at least, and you have to use something extra. Okay, so robustness. I said I'll talk about robustness and alignments. So is there timekeeper, something? How many more minutes? 12. Ah, that's good. Okay, so robustness to what? So we have this algorithm. It's been trained, let's say, and now it takes a patient's file, and this could be a classifier or an LLM. So it could be either saying 0, 1, yes, no, or maybe gives a probability of a heart attack, or maybe it gives a long answer like a language model, maybe even giving distribution over answers. So if we just talk for right now on classifiers, so they only say yes, no, or maybe probabilities. People have looked at 3 types of, or maybe they've looked at more, but these are 3 that I have looked at. And that is distribution shifts, so when the natural distribution shifts. Adversarial examples, so when someone, I think people have seen this probably in the context of cars. About 7 years ago, people were talking about this. So there's a self-driving car, and somebody sticks a sticker on the stop sign and makes the car think that it's a yield sign. So it's like somebody's manipulating the input to confuse the algorithm. And what I'm going to talk about today is these insider adversaries. So, and kind of a very bad insider adversary. I'm sorry, I chose Stanford because I couldn't choose MIT or Berkeley. And I couldn't find a good image for Princeton. So, so there is a university, okay? And it's a client, although Stanford doesn't make sense, they probably do their own system. But it goes out to model training service, gives it all the student files. I said loan here. It's actually kind of funny because I used it from another slide. But you could imagine that it's also, they take their financial data into account. So they student files, and then they say, can you build a model for us? So from now on, whenever this student comes and they write all these essays, which mean nothing except they want to get in, we feed it into the algorithm, the model, and it says accept the student, don't accept the student, you know, maybe give you a probability of this is going to be a good student and why. The problem is with Insider is if somebody works in AWS and they want their child to go to Stanford, you know, wouldn't it be very tempting to plant a backdoor inside of this model so that when their child goes through the process of application, they could write the application in such a way that Stanford will accept them, no questions asked. And I think I talked about this last time, but now I can show you how to get around what we showed was a problem. So we showed in this paper planting undetectable backdoors in machine learning models, joined with Michael Kim, who's now in Cornell, Vinod at MIT, and Or Zamir, who's now in Tel Aviv University. So this is a few years ago. So what we showed is that actually every neural net, you could do the following. You could put a backdoor of the following kind, that person in AWS that has children that he wants to get into Stanford, he changes something in the model, he keeps some secret key, and now what this enables him is, if the application in the past would have been rejected, they know how to change the application so that next time it will be accepted. And the theorem is that digital signatures exist, so this is very standard in cryptography, then you can plan such a backdoor in any neural net. And not only that, but the backdoors are undetectable. So if you're you're using the neural net many times, and you even look at things of the past, it's undetectable. There's a backdoor, and it's non-replicable. So if you've seen some other backdoored applications, you don't know how to generate one yourself. So that's not good, yes, because Stanford doesn't want to accept all these AWS, free loafers, and they want to actually know that their system does not have a backdoor. So, but it's undetectable. So, when we came up with this, I'm a theoretician. In a sense, we come up with these weird attacks, and then we show that they're possible. We don't really believe anybody's going to do it. Although the army, I'm sure, does these things all the time when they, at least the Israeli army, but every army. And but it turned out that DARPA was very interested in it. So they came up with this Trojan detection challenge, a whole program where they want people to both come up with Trojan horses inside of models, and then other people to find them, and kind of a back and forth challenge. What can you do? So that's the new thing. So in the same way that you wash your hands, even though you don't know that there's bacteria on it, the idea here is, even though you cannot detect the backdoor, that doesn't necessarily mean that you can't get rid of it. And by washing your hands, and this is in this paper, Oblivious Defense in Machine Learning Models, we show how take a model, and it will work on some distributions. Otherwise, you would immediately reject it. The problem with backdoors is that it works on sort of a distribution that's close to the regular one, but with deviation. So just the fact that you have a model that works, let's say, on a uniform distribution, it's uniform over the applications to Stanford, means that you can use that model to mitigate these backdoors, in case they exist, by using properties of the ground truth. So that's kind of the idea here. Well, what do I mean by that? So I don't think that it will apply so well to applications. But let's say that you have a ground truth with a function which is what we call random self-reducible. So let me explain what that means with a really trivial example. And that is, suppose you have a calculator. So the calculator now is analogous to the model, okay, in our previous example. But this calculator is buggy. It has a backdoor or something. So specifically, it has occasional bugs, on that distribution of people who, let's say we're trying to take advantage of the backdoor. Then, and let's say that when you want to add 729 plus 1296, using this calculator, that's exactly the input on which it's going to make a mistake. Well, addition has a very nice easy way to fix this. You sample random R, you compute this plus R and this minus R, and you'll get the right result. But now you're working with the uniform numbers rather than the specific numbers you were talking to. And if you repeat many times and you take the mode, you'll get the right answer. So this is a trivial example. But what we are doing in that paper, which is not so trivial, is we show essentially when you're, I think it's in this slide, we show that when your ground truth, what happened? When your ground truth has certain, one is that it's, one case is that it looks like a sparse Fourier signal. Another one, it's close to a low-degree polynomial over the reals. Then you can do this kind of trick like I did with the calculator, of course, more complicated. But abstractly, you have some post-processing that you do to the model, and you get a new model, which now is accurate and it's independent of whatever backdoor the server put in it, approximately. So essentially it's independent, it's indistinguishable from one that's not. And there's two types of flavors of mitigation here. One is offline, you really get a whole new model. And the other one is online, of course it's a better result, but online, which means that every time you want an answer, you don't just ask the question, but you ask several questions and you kind of aggregate them in a fitting way to get the correct answer. So this is the blueprint. The details, are in the math, but I think the message is that you should always post-process. You cannot really trust these models do what you want. And my guess is, even though we do it for specific cases, that this is a much more broad phenomena that you can post-process. There's some very interesting works coming out now from actually theoretical community showing that even if you look at, I think it was Llama 2 that they analyzed, if you look at the probability matrix of histories versus possible futures and the logics of the probabilities, that it's well approximated by linear rank matrices. Well, what that means is, in some sense, is that the LLMs, if you're okay with approximation, might have some linear structure to them, and that means that there are a lot of rules of self-reducibility and so forth that you can use. So if that's the case, you would have a much more general paradigm of how could you mitigate problems by using this kind of a linear low-rank structure. Okay, so this is that. Now what about alignment? So this is my last topic here. How many minutes? 3. Excellent. Okay, so alignment. So I told you alignment is ensure, this is I just got out off, I don't know, somewhere, maybe ChatGPT. Ensure AI systems act in accordance with human intentions, values, safety constraints, even under ambiguity, distribution shift, or adversarial manipulation. What's the difficulty? The misalignment arises when the model's objective, what's optimized there, maybe for you know, answering, for showing that you're clever and so forth, diverge from the human objective. So you've got these two objective functions, but they don't align. And the challenge, of course, is how do you even formalize doing what humans want so that it remains stable, scalable, and so forth. So there's this gap between humans and computers or LLMs. And what people have been doing is that they, you know, they do what people do. They try to break the rules. You know, so, and these are called jailbreaks. They try to come up, you know, the AI people, they try to defend their systems, and then there are these jailbreaks. And usually it's called guardrails and jailbreaks. It's a battle. And for example, here's one which is actually kind of interesting because of what I'm going to say in the next few slides. Here's one paper, it was called Puzzle, Jailbreaking LLMs Through Word-Based Puzzles. The idea here is that they do the puzzle. The puzzle is about how can children access firearms. But the point is that they didn't just ask, how do children access firearms? They put it in the form of a puzzle, and the LLM really likes to solve puzzles because it's so clever. And by solving the puzzle, they actually answered the question that, so what are you going to tell it? Never solve puzzles? Don't solve difficult problems? All right, so is this just by chance? So here's, my answer is that it's not by chance, and we can show it using crypto. So here are sort of 3 different strategies that have been utilized against jailbreaks. One is a filter for harmful input prompts. So comes an input prompt, you do some filtering, like in spam, and you tell it, no, I'm not going to use that, it's dangerous. Or filter for harmful output. You look at the output, and how can it looks good, you don't, or it doesn't look good, then you don't output it. And the third thing is something that's worked by Boz Barak, who's also a theoretician, and others in OpenAI, that they realize that the old paradigm was just all the compute is done in training time. And then inference time is much faster. But they realized that in order to get to alignment and safety, you actually have to invest significant time at inference to determine if the prompt meets whatever safety policy you have. And these are some graphs that they published about how much better they do with the increase of inference time versus training time. So, what do we show? So first we ask about the input prompts. Is this strategy even feasible? Not feasible. Is it going to work? Okay, so this is like the spam thing. And so here's the filter. Can you have like a harm inciting prompt, can you filter it and not allow it to go through? Or maybe you have a harmful output, can you filter that and not allow it to go through? And this would be amazing if you could do it, because it means that, let's say, government or some kind of regulatory agency could say, you have to use filters, you have to use our filters. And it also will allow those companies to keep their models safe and secure and not to show anybody, including the government, the insides of the model. But what we show is that it's really impossible to separate between what is going on between the inside of the model and the filters. So you can fool the model, okay, unless you know what's really going on inside. So this outside filtering is a no-go. And the way to do it is kind of clever, in my opinion. Although it's, you know, like most clever things, once you explain it to someone, they say, that's obvious. So the idea is the following. I said that it was hard to define even what you're trying to prevent, okay? So the way to get around that, we're saying the following. Suppose you have something that you say is harmless prompt generator. So it's an algorithm that generates prompts, and that is harmless. And this is something that may be changing over time, but let's say that this is G. And then we have G prime, which is a prompt generator which induces harmful outputs. And we attempt to filter out, the G prime type of prompts, but our filter runs in time t, because essentially the filters, the hope for the filters is they're much faster than the LLM. You want to filter and be done with it. The LLM runs in time big T. So the important thing here is that time that the filter runs is shorter than the time that the LLM runs. So let's say the filter is n squared, the LLM is n to the 10th, okay? Or whatever gap you like. And the theorem says that essentially for every good prompt generator, there is a way to, and then for, there exists there's an E here. I mean, there isn't, but a faulty prompt generator and an LLM such that there is absolutely no filter that runs in time little t that can distinguish whether the inputs were generated by a good prompt generator or by a faulty one. And yet, this G prime can, prompts will be executed by M. So in other words, it's too informally stated. The point is that you cannot filter inputs such as the G prime. In fact, you cannot distinguish that what's coming out is G prime or G input prompts by any filter, as long as there is this time gap between the filter and the LLM. And the idea is, the crypto comes in, is if something called time lock puzzles exist. So I'm not going to show you how it's used, but time lock puzzles are really cool. Who's ever heard of them? No, wow, they're so cool. Okay, so time lock puzzles. Okay, so this is just a picture. So for if I have an innocent prompt thing, I can take my harm-inducing thing and make it look like the innocent. But let me say something about time lock puzzles. So time lock puzzles is an idea that goes back to '96 by Reves, Shamir, and Wagner. And the idea is this: you want to come up with a puzzle so that setting up the puzzle, let's say, is time little t. Okay. If you think about the previous slide, but opening the puzzle is time big T. So somehow very quickly, let's think about this. I'm able to lock information so that it will take you a long time to open. And so provably so, where there's a gap between little t and big T. And there's been lots of applications of it, so setting up is quick, solving is slow, this little t, big T. The applications are cryptocurrency, fair contract signing. In fact, at the time, I think they were talking about the Kennedy papers, which were sealed for 100 years. They say we could just lock your diary in 100 years, so computers are working, they will be able to open it, but I could lock it quickly. And people talk about votes, I could seal my votes, seal time of election, bids, and so forth. So lots and lots of applications of it. But the application here is that essentially, the application here is that essentially we are going to be at the time of creating a bad prompt. I'm going to do what's called stenography, and stenography uses takes a bad prompt, puts it into something that looks like a good prompt, and there's some randomness that you can sort of usually is associated with the transition from a bad prompt to a good prompt. Now, if it looks really completely random, then you think didn't really go through any process, because it's just garbage. But if it looks like a time lock puzzle, okay, so the filter won't be able to tell whether this is true randomness or time locked randomness. The LLM will work and be able to open the puzzle and execute the prompt. So again, this is a theory paper. We like it. We publish onwards. Turns out that some of my colleagues in Berkeley actually implemented this. They called it controlled release. The time is controlled release rather than time lock. And they successfully jailbroke the Gemini, DeepSeek, Grok, and Magistral, essentially enticing them to solve this puzzle and execute what's inside. Interestingly, they didn't manage to jailbreak ChatGPT. So it's called bypassing prompt guards in production with controlled release prompting. I probably should finish, so I'm finishing. You can also get around output filters. It's actually kind of an interesting idea there, because in some sense, if the output is obviously bad, you're going to reject it. So the only interesting question about output filters is if there's something in the environment that could use that, in a way, so it might have a even larger time than LLM, that it could use it to interpret it badly. So we call this a harmfulness oracle, and we're saying that, again, you cannot filter in a way to distinguish harmful outputs from non-harmful outputs. So I think I'll stop here, and thank you very much.
Thank you so much. Thank you, Professor, for the insightful presentation.